Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 48. In this lecture, we'll discuss heat capacity and adiabatic processes. These topics are covered in Chapter 21 of our textbook by Surway and Jewett. In this lecture, we want to discuss heat capacity. Now, we've already discussed heat capacity before, but in this lecture, we want to refine the concept considerably. Let me first review with you what we have already discussed. Recall that we were interested in the following question. How much heat must we add to a substance to change its temperature by a certain amount? The answer to that question is provided by the specific heat equation. Here, Q is the amount of heat that must be added. M is the mass of the substance that you're trying to heat up. Delta T is the change in temperature that you want to achieve. And lowercase c is referred to as the specific heat capacity of the substance. It's a number that's different for different substances in different phases. For copper, for example, the specific heat capacity is 387. This means that we would need 387 joules per kilogram of copper to raise its temperature by 1 Kelvin. For water in its liquid phase, the specific heat capacity is 4,186. So we would need approximately 4,000 joules of energy for each kilogram of water to raise its temperature by 1 Kelvin. Now, up until now, you've simply had to look up these numbers in a table. These numbers are often measured carefully by material scientists in the laboratory. However, as we will see later in this lecture, some of these numbers can be calculated if we know the degrees of freedom for the substance. I've also explained before that in this context, one sometimes encounters lowercase c and sometimes uppercase c. Lowercase c refers to the specific heat capacity of some substance, while uppercase c refers to simply the heat capacity. What makes lowercase c specific is the fact that it specifically refers to 1 kilogram or 1 unit of mass of some substance. So if you know the specific heat capacity for some substance, you can then multiply it by the mass of an object to find the heat capacity for that object. We sometimes describe the situation by saying that the specific heat capacity refers to a substance or material, while heat capacity refers to a unique object. Otherwise, the two concepts are very closely related. However, going forward, you need to be vigilant for this word specific. We have to refine these concepts considerably if we want to start using heat capacity in precise calculations. To begin with, there are at least 3 different types of heat capacity that you need to be aware of. First, there is ordinary heat capacity, which we denote using uppercase C. It shows up in this formula where Q is the amount of heat required to change the temperature of an object by delta T. When I put square brackets around the quantity, I'm referring to the unit for that quantity. The SI unit for heat capacity is simply joules per Kelvin. There's also specific heat capacity, which we've discussed before. Specific heat capacity shows up in this equation, and the SI unit for specific heat capacity is joules per kilogram per Kelvin. In addition to these two, there's also molar specific heat capacity, which we will denote using C prime. The prime in this context simply indicates that this C is slightly different from this C. Note that while specific heat capacity refers to mass, molar specific heat capacity refers to the number of moles. The SI unit for molar specific heat capacity is joules per mole per Kelvin. Many textbooks use the same exact letter for both specific heat capacity and molar specific heat capacity. They rely on the context or the units to distinguish the two. However, to be precise, you really should use slightly different notation for these two heat capacities. It turns out the notion of heat capacity is even more complicated than this. heat capacity depends on how exactly the object is heated. A little more specifically, which of the four fundamental thermodynamic processes do you wish to use as you heat the object? If you want to use an isothermal process, then the notion of heat capacity is not relevant because by definition in an isothermal process, delta T is equal to 0. If you want to use an adiabatic process, again, the notion of heat capacity is not relevant because by definition, in an adiabatic process, Q is equal to 0. The notion of heat capacity is relevant to an isochoric process. It's also relevant to an isobaric process. However, in these two cases, each one has its own heat capacity. So the heat capacity in an isochoric process is different from the heat capacity in an isobaric process. Let's examine that difference in more detail. Once again, we're interested in the following questions. Suppose heat Q is added to a system. How much does the temperature change? In our previous lecture, we learned about the equipartition theorem. From the equipartition theorem, we know that the change in the internal energy of a system is equal to the number of moles times the degrees of freedom times 1/2 R delta T. The first law of thermodynamics states that the change in internal energy of a system is equal to heat plus work. Now we can take these two expressions for the change in internal energy and set them equal to each other. By setting them equal to each other, we find that the change in the temperature is equal to 2 divided by NdR times the quantity Q plus W. Now W here is work, and we've calculated the work performed in each of the four thermodynamic processes before. Specifically, we know that in an isochoric process, work is equal to 0, and in an isobaric process, work is equal to minus P delta V. In an isobaric process, the pressure is constant, so the pressure that's often used is simply the initial pressure of the system. Now we can take these two expressions for work and substitute it into this expression for delta T above. When we do that, we find that the change in temperature for an isochoric process is different from the change in temperature in an isobaric process. A little more specifically, since the work performed in an isobaric process is a negative number, we find that delta T is going to be a smaller number for an isobaric process. We can describe the situation by saying that in an isobaric process, more heat is needed to raise the temperature because some of the heat is effectively wasted performing work on the system. That work refers to this negative quantity here. To better understand the differences between isochoric and isobaric processes, let's do a side-by-side comparison. To begin with, recall what we're trying to do. We have some volume of ideal gas and we're trying to change its temperature by adding some heat to it. The volume of gas is confined to a cylinder and the cylinder is capped by a piston. In an isochoric process, the piston is basically bolted or fixed in place. That way the volume of the gas is not allowed to change and we can say delta V is equal to 0. In an isobaric process, the piston is free to move up and down. However, we will place a fixed weight on top of the piston. That weight applies a fixed and constant force to the piston, and therefore we can say that the pressure of the gas is constant, or that delta P is equal to 0. Now, by using the equipartition theorem and the first law of thermodynamics, we find that Q is equal to Nd 1/2 R delta T minus W. In an isochoric process, W is equal to 0, so we find that Q is simply proportional to delta T. This equation suggests that all of the added heat goes into changing temperature and none goes into changing the volume. The situation for an isobaric process is a little different. Once again, we can equate the equipartition theorem and the first law of thermodynamics to find that Q can be expressed as shown here. Work in an isobaric process is minus P delta V, so now we find that heat is proportional to both delta T and delta V. This equation suggests that some of the added heat goes into changing the temperature, but some also goes into changing the volume. The amount of heat that goes into changing the volume is basically wasted heat if your goal is to primarily change the temperature. We can describe the situation by saying that raising temperature requires less heat in an isochoric process, while raising temperature requires more heat in an isobaric process. A little more precisely, we can now define two kinds of heat capacity, the isochoric heat capacity and the isobaric heat capacity, and we can say that the isochoric heat capacity is always less than the isobaric heat capacity. The subscript V denotes an isochoric process where the volume is fixed or constant. The subscript P denotes an isobaric process where pressure is constant. What we have shown is that quite generally the isochoric heat capacity is always less than the isobaric heat capacity. If you've been paying careful attention to our calculations, you may have noticed that we can actually do a lot better than that. We can actually calculate the isochoric and isobaric heat capacities. To do that, we'll start with the equipartition theorem. Quite generally, according to the equipartition theorem, the change in the internal energy of a system is equal to the number of moles times the degrees of freedom times 1/2 times the gas constant times the change in the temperature of that material. Now, for an isochoric process, we know that work is equal to 0. More specifically, for a process in which the volume does not change, the thermodynamic work must equal to 0. Now we know that according to the first law of thermodynamics, the change in internal energy is equal to Q plus W. By rearranging that equation, we find that Q is equal to delta E minus W. Now we know that for an isochoric process, W is equal to 0. We can substitute that in here. And we have this expression for the change in internal energy. We can substitute that in here. And we find that Q is equal to ND 1/2 R delta T. Now, by definition of molar specific heat capacity, we know Q is equal to NC prime delta T. Q is the heat that's required to change the temperature by delta T, and C prime is the molar specific heat capacity. Now notice that we have two expressions for Q. We can set these two expressions equal to each other. When we set these two expressions equal to each other, we see that the number of moles cancels out. We find that the change in temperature cancels out. And then what we have left is something very interesting. We find that C prime must equal to D times 1/2 times R. So what we have done is, in fact, derived an expression for the molar specific heat capacity of a substance. What we're finding is that the isochoric molar specific heat capacity, which is the amount of heat required to raise the temperature of 1 mole by 1 degree at constant volume, is given by this expression here. So we no longer have to refer to a table to look up the molar specific heat capacity for a substance. If we know what the degrees of freedom are, we can just divide that number by 2, multiply by the gas constant, and amazingly, we find the isochoric molar specific heat capacity. We can do a similar calculation for isobaric processes. Once again, we start with the equipartition theorem, which states that quite generally for all processes, delta E internal is equal to ND 1/2 R delta T. Specifically for an isobaric process, we can calculate the work that is performed, and we find that W is equal to minus P times delta V. Since we're talking about an isobaric process, the pressure is not changing, so people often substitute the initial pressure into this expression, knowing that that pressure will not change. Now we are talking about an ideal gas here, and we know that for an ideal gas, PV equals nRT. Using the ideal gas law, we conclude that P delta V must equal to nR delta T. By the first law of thermodynamics, we know that delta E internal is equal to Q plus W. Rearranging that expression, we find that Q is equal to delta E internal minus W. We can now take this expression for work and substitute it into the first law of thermodynamics, and this expression for the change in internal energy, and substitute that in here, and find that the heat that is required to change the temperature by delta T in an isobaric process is given by the expression you see here, d over 2 plus 1, that quantity times nR delta T. Now, by definition of molar specific heat capacity, the heat that is required must equal to the number of moles times C prime times delta T. Once again, we have two expressions for heat, and we could set these equal to each other. When we set those equal to each other, we find that the n's cancel out, the delta t's cancel out, and we find a nice expression for C prime. So what we're finding here is that the isobaric molar specific heat capacity can be expressed by this expression here. Remember that Cp prime is the amount of heat required to raise the temperature of 1 mole by 1 degree at a constant pressure. So once again, we don't need to refer to a table, we only need to know the degrees of freedom for the substance that we're interested in, and if we know what that number is, then we can calculate how much heat it takes to change the temperature of that substance in an isobaric process. Over the last few lectures, we've derived quite a few important results, which I now just want to summarize in one place. One of the first results that we found was that the pressure of a gas can be expressed in terms of the average kinetic energy of the molecules of that gas. So if we know the mass per molecule and we know the average speed squared per molecule, then we can actually calculate the pressure of a gas of those molecules using the average kinetic energy, the number of molecules, and the volume to which the gas is confined. Using that same information, we can also calculate the temperature of the gas. What this is telling us is that these thermodynamic parameters, like pressure and temperature, really are related to mechanical parameters such as kinetic energy, speed, and mass. Another important result is known as the equipartition theorem. The equipartition theorem allows us to calculate the internal energy of a gas. For that purpose, we need to know the degrees of freedom of the gas, which normally depends on the types of molecules that we have. Monatomic, diatomic, and triatomic molecules have different numbers of degrees of freedom, but if we know what that number is, then we can calculate the internal energy of the gas. We can calculate that internal energy in terms of the number of particles or the number of moles. In this lecture, we have found expressions for the heat capacity of materials. Although we should be a little more precise, what we have found are two equations for the specific heat capacity of a substance as it is heated in an isochoric process or an isobaric process. Notice that these specific heat capacities are molar specific heat capacities and that they depend on the degrees of freedom. Also note that we don't talk about heat capacity in the context of adiabatic or isothermal processes because in those processes either Q is equal to 0 or delta T is equal to 0, so it doesn't make sense to talk about a change in temperature. Before concluding our discussion of the kinetic theory of gases, I want to present one last result. This final result, which is known as the adiabatic condition, states that for an adiabatic process, pressure times volume raised to the gamma power is constant. In other words, throughout an adiabatic process, no matter how the pressure and the volume are changing, this particular combination will always remain constant. In particular, whatever its value at the beginning of the process was, it will retain that value throughout the process. So this constant here is often written as P initial times V initial to the gamma. This equation is useful because it allows us to calculate the final pressure in an adiabatic process if we know the final volume. A little more precisely, we can express this equation by saying P final times V final to the gamma is equal to whatever the initial value of this particular combination was at the beginning of the process. If we now know what V final is, we can use this equation to find the final pressure in an adiabatic process. The exponent that you see here, gamma, is referred to as the specific heat ratio. It's known as the specific heat ratio because it is defined as the ratio of two specific heats. More precisely, gamma is the isobaric molar specific heat capacity divided by the isochoric molar specific heat capacity. Now we've derived expressions for these heat capacities, so we can actually calculate gamma in terms of the degrees of freedom. We know that Cp prime is given by this expression in terms of d, which is the degrees of freedom. We know Cv prime is given by this expression. Canceling out the gas constant from the numerator and the denominator and simplifying the expression, we find that gamma, the specific heat ratio, can be written as 1 plus 2d. So knowing the type of molecules that we have, we can calculate the degrees of freedom, and from that we can find gamma, and therefore we can use the adiabatic condition. For monatomic ideal gases where d is equal to 3, gamma ends up being equal to 5/3. For a cold diatomic ideal gas where d is equal to 5, gamma ends up being 7/5. For a hot diatomic ideal gas, d is equal to 7, and that means that gamma is equal to 9/7. Let's do a practice problem now with some of the ideas we have just learned. 3 moles of a cold diatomic ideal gas initially has a volume of 4 cubic meters and a pressure of 300 Pascal. The gas is allowed to adiabatically expand to twice its initial volume. Calculate the final temperature and pressure of the gas. Note that there's a lot of information that's provided in this problem. We have 3 moles of this gas, so we can immediately say that lowercase n is equal to 3. We have a cold diatomic gas, which means the degrees of freedom is equal to 5. It is an ideal gas, which means that PV equals nRT. In other words, the gas obeys the ideal gas law. The initial volume is 4 cubic meters, so we can write V initial is equal to 4, and the initial pressure is equal to 300. Notice that these are in SI units, so we don't need to do any unit conversions. The gas is allowed to adiabatically expand to twice its initial volume, and what that means is that its final volume is going to be equal to 8 cubic meters. What we now want to calculate is the final pressure of the gas as well as the final temperature of the gas. Notice that this process is carried out adiabatically, so we can use the adiabatic condition to answer this question. Since the gas is a cold diatomic gas, the degrees of freedom is going to be equal to 5. Based on that information, we can find gamma. The specific heat ratio is equal to 1 plus 2 divided by the degrees of freedom. In this case, that comes out to be 1.4. For an adiabatic process, we know that this particular combination, PV to the gamma, remains constant. Whatever that particular combination was at the beginning of the process, it must still hold at the end of the process. So we can use this equation to solve for P final. P final is equal to P initial, which is given as 300, times V initial to the gamma, so we have 4 raised to the 1.4 power, divided by V final to the gamma, so we have 8 raised to the 1.4 power. Plugging those numbers in, we find that the final pressure of this ideal gas must be 113.679 pascals. Now the question also asks for the final temperature of this gas. We know that the gas is an ideal gas, so it obeys the ideal gas law. In particular, P final times V final must equal to nRT final. Rearranging that equation, we find that T final is equal to P final, which we just found here, V final, which we know is 8, divided by nR. R is the gas constant and lowercase n is the number of moles. We know that's 3. Plugging those numbers in, we find that the final temperature of this gas must be approximately 36 Kelvin. Let's end this lecture with one last practice problem. 2 moles of a hot diatomic ideal gas are to be heated from initial temperature 20 degrees Celsius to final temperature 50 degrees Celsius. Calculate the heat required in each of the following processes. In process A, the gas is confined to a rigid container of volume 48 liters. In process B, the gas is confined to a flexible balloon of volume 48 liters. Now, these 2 processes sound a little mysterious, so we need to think about them a little more. Notice that for process A, the gas is confined inside a rigid container. What that means is that the walls of the container are fixed in place, and therefore the volume of the gas cannot change. If the initial volume of the gas is 48 liters, then the final volume of the gas in this process, as we heat up the gas, is also going to be 48 liters. So process A is really a process in which delta V is equal to 0. Now, in process B, the gas is confined to a flexible balloon. A flexible balloon can easily expand as the temperature of the gas is raised. The walls of the balloon will expand so that the pressure inside the balloon can be in equilibrium with the pressure outside the balloon. Since the pressure outside of the balloon is atmospheric or ambient pressure, it is assumed to be constant, and what that means is that the pressure inside the balloon will also remain constant throughout this process. So process B is really describing a process in which the pressure does not change. So secretly, we're really describing an isochoric process and an isobaric process. We have a hot diatomic gas. We know that for a hot diatomic gas, all degrees of freedom are active, and therefore D is equal to 7. We know that for an isochoric process, CV prime is equal to the degrees of freedom divided by 2 times R. Plugging 7 into this equation, we find that the isochoric molar specific heat capacity for this gas is approximately equal to 29 joules per mole per Kelvin. This allows us to calculate the heat that is required to change the temperature by 30 degrees Celsius. N is 2, CV prime is approximately 29, and delta T, of course, is the difference between the final and the initial temperatures. We find that for this isochoric process, we need 1,745.94 joules of energy. Process B is an isobaric process. We know that for an isobaric process, Cp prime is equal to D plus 2 divided by 2 times R. R is the gas constant, and D is equal to 7. Plugging those numbers in, we find that the isobaric molar specific heat capacity is equal to 37.413 joules per mole per Kelvin. With that information, we can now find the amount of heat that is required to change the temperature by 30 degrees Celsius in the isobaric process. Plugging the numbers in, we find that we need 2,244.78 joules to increase the temperature of the gas inside the balloon by 30 degrees Celsius. Note that, as we suggested earlier, the amount of heat required for the isobaric process is greater than the amount of heat required for the isochoric process. And that is the end of this lecture. Thank you for your attention.